questions. So let me just recap quickly. We have chapter 2, beginning with capacitors, not capacitors in the area and all that business, just capacitors in series and parallel. And then also caps and combination circuits. We can look at some of those in just a bit. That's the end of chapter 2, right? And then we go into chapter 3, which is Ohm's law, current, definition of current, power, P equal VI. That carries on into chapter 4 as well. And then in chapter 4, we have, and then also in chapter 3, we had resistance. And then in chapter 4, we have circuits, we have resistors in series and parallel. We have combination circuits where they're in both series and parallel. Then we have multi-loop circuits. After multi-loop, we have RC circuits and household circuits. Just basic information about those. So these are the big ones. We have chapter 2B, 3, and 4. And all of that's going to be on the test. We'll have something on all of that. All right? What in particular is difficult, most difficult for you?
Like for me, like the multi-loop, I don't know.
The multi-loop circuits? Okay, yeah, a lot of students are having trouble with that. So why don't we take a look at multi-loop, and then y'all can think about sort of where you're deficient. But multi-loop, you'll have several problems on multi-loop circuits. So with multi-loop circuits, we need to know the junction rule. And the junction rule just says that the incoming current equals the outgoing current. All right, so like if I have several currents, say I have 4 amps coming in here, if this is 2 amps, then this also has to be 2 amps because the incoming current is 4, the outgoing current is 2 plus 2. That's the junction rule. And then the loop rule says that the sum of the potentials across a closed loop is equal to 0. And then with the loop rule, we had several guidelines. If I have a resistor, I'm going from this point A to point B. If the current is in this direction, then the potential is equal to negative IR. If I'm going with the current, the potential is negative. If I'm going against the current's in this direction, but I'm still going from A to B, then the potential is positive IR. So with resistors in multi-loop circuits, you have 2 directions. You have the direction of the current and the direction that you're traveling through the circuit. And then the other thing that you have is for batteries. So if I have a battery and I'm going from little to big side, then that's a positive change in potential. If I'm going from big to little, that is a negative change in potential. So let me give you an example. We'll work through it. Apply those rules.
Like the current from the battery normally goes from like the high and then like it goes around. That's the way the current goes. Or like can it be different?
Repeat what you just said.
Like the current, you know, like when you have the high and the positive. Like it goes this way.
Normally, yeah, if I have a battery, normally the current will come off the battery off of that high potential side. But if I'm looking at a multi-loop circuit, well, let's just do an example. Is that okay? So let's do an example where I have let's say this is 2 volts, 3 volts, 4 volts, 1 ohm, and 2 ohms. All right, I want to write the loop rule. So I want to write the loop rule for, say, the top loop, and for the bottom loop, and the big loop, and then the middle loop. Now on the test, you'll have 2 different things. You'll have those problems where I give you an equation that has the currents labeled on it, and you'll have to find the correct or incorrect equation. I think it's correct. The correct equation, okay? Where you just trace through and you find out which equations are correct or incorrect. Then you'll have another problem where the currents won't be labeled at all, and you'll have to find a current through a given device. I'll say, what is the current through the 1 ohm resistor, for example. Okay? So in those, you'll have to determine what is the direction of the current. So you'll just pick a direction. So I'll start here. I don't know, it doesn't really matter what I pick. I'm just going to say I1 is in this direction. That means that I1 goes through that part of the circuit. I2 doesn't matter. I'll just say I2 goes in that direction. And then I3, let's say that I3 goes in that direction. Okay? So I3 then goes to that bottom half of the circuit. Then if I write the equation for the top loop, this is I1 right here. If I write the equation for the top loop, I pick a direction now to travel through the circuit. So let's say I start here and I go in this direction. And I'm going to have plus or minus 2? Plus 2. Coming along here, plus or minus what? Minus 1 ohm times I2. And then plus or minus 3? Plus 3. That's equal to 0. So that completes the loop. So that is the loop rule for the top loop. For the bottom loop, I don't know, I could start right here and go in this direction. I would have minus 3 plus I2. That's 1 times I2. Minus 4. What's the last one? That's right. Okay? So now I've written a loop rule. You could do a loop rule for the big loop, and then you could also write a junction rule. For the junction rule, you just pick any old junction. There are only 2. You just pick a junction here, over here. Let's do the one here on the right. What are the currents going into this junction on the right? Well, I1 goes into that junction. I2 also goes into that junction. So I'll say I1 plus I2. And I3, notice, goes in this direction out of that junction. That's equal to I3. You'll also need to look for that appropriate equation in that where I give you a bunch of equations. And you have to pick one. Okay? So those are multi-loop circuits in a nutshell. The other thing, though, that you'll need to do is, given a multi-loop circuit, find the current. So let's say, for example, I wanted to know the current through this resistor. How would I find that? Which loop would I use? I've used the top loop. Why would I use the top loop? There's no resistor, right? Because I have no resistor here, so I1 would never come into the top loop equation. By the way, if I wanted to find I1, even though there's no resistor, I'd have to go back to my junction rule, but you don't have to worry about that. You will see that. So here, if I wanted to know the resistance or the current I2, I would just use this equation. This was our top loop equation, and solve it for I2. Another way to make these multi-loop circuits easier is I would just give you a current. So like, for example, if there was a resistor up here, then we would have I1 in this equation, and I would just say, find I2, but by the way, I1 is, well, whatever I1 is.
Would you wonder what the magnitude is, if like 1 up or 1 down, like that kind of problem?
1 up or 1 down?
Like it was like you find the current.
Well, let's just do this one. Well, if I find I2 here, I understand what you're asking, but let's find I2. I think this is what you're asking. So here I would find I2. I'd have negative 1 I2 is equal to negative 5, and so I2 is equal to 5 amps. And then I go back and I look at the direction of I2. I had chosen I2 to be to the right, so it is to the right because this is positive. However, if I2 had come out negative, then I would just say, hey, it's not to the right. I chose that direction incorrectly, so it must be to the left. Is that what you're asking? Yeah, so when you're looking at the direction, and that will be important because that'll be part of the problem, I'm pretty sure. I think it's important because if the value comes out to be negative, it didn't here, but if it did come out to be negative, then the direction would be the opposite of what we found it to be. Because remember, you're just picking random directions. It doesn't matter what direction you pick. If you pick them incorrectly, then in the end, it will come out negative. Does that answer your question?
Yeah.
It's a good question.
For the junction rule, that's used for the I1 plus I2 and I3.
Right, this is the junction rule right here. The incoming current.
Still not sure how do we use that.
Oh, well, honestly, like, you're not gonna use it on the test. You might see it in the equations, where you have to pick out the right equations. But as I said, in this circuit, for example, if you wanted to know I1, since there are no resistors in the top branch, the only place that I1 occurs in any equation is right here. So you'd have to use this as an extra equation to solve a system for I1. But as far as you're concerned, don't worry about it, except that you're able to write the appropriate junction rule. Okay? If you're solving the full system of equations like you do in your homework, it would be important, but here it's not. Okay? Those are multi-loop circuits. I think there are, two or three questions maybe? I forget. Two or three questions. I sent y'all the distribution out. Okay? You will also have combination circuits, resistors in series and parallel, which I consider a different topic. All right, what next? Anything? Combination circuits, okay. So, and this is important too for capacitors. Don't forget capacitors are on here. Be careful because the capacitor circuits are similar but different. So make sure that you can keep them straight in your mind. It's a little unfortunate that they're both on this exam, but it's good too because they're a lot alike. And if you can understand capacitor circuits, then you can probably master resistor circuits as well. So let's just work through an example. Let's say that I have 12 volts. Shoot, what is that? All right, let's do this. All right, I want to know what is the equivalent resistance, and I also want to know what is the current through any one of the resistors. You should be able to answer any one of those. So to begin with, to find the equivalent, I pick either of those that are just in series or just in parallel. I can start in one of two places here. I can start here, or I can start here. The equivalent of this is what? The 2 and the 2? 4. Is 4. I add up 2 plus 2 is 4. That gives me a 4 and a 4. Which is 2 is right. 1 over a quarter plus a quarter is 1 over a half, which is 2. So my 2 and my 2 become 4. My 4 and my 4 become 2. These two become 4 ohms. And then combined here, I have a 4 and a 4. It becomes 2 ohms. And so I can redraw my circuit, start redrawing it. I have 2 ohms. And then the 8 and the 8, what does that become? 1 over an eighth plus an eighth. Well, an eighth plus an eighth is 2 eighths, which is a fourth, which is 4. All right, so I have 4 ohms here. And then this is 12 volts. Can you tell me what the voltages are on the 2 and the 4? Well, one is twice that of the other. 8 and 4. Which is 8? 8 volts and 4 volts. Be careful, it's different for capacitors. For capacitors, the small capacitors have a big voltage. For resistors, the big resistors have a big voltage. V equals IR. So if R goes up, V goes up. Huh? Yeah, I know. That's an unfortunate thing. I wish that capacitors were different, but that's just the way they are. Notice that 4 plus 8 equals 12. That's part of our loop rule. By the way, if you weren't so clear on that, notice the 2 and the 4 give me 6 ohms, 12 volts. So my current here is 2 amps. So I have 2 amps here and 2 amps here, because resistors in series have the same current. So I have 2 amps going through both of those. V is equal to IR, so I times R equals 4. I times R equals 8. Okay? And then that's it. I mean, we can step back from there. If this is 8 volts here, I also have 8 volts here and here, because resistors in parallel have the same voltage. If this is 4 volts here, I have 4 volts here. What do I have on the 2 ohm resistor up here? I have 2 volts and 2 volts. Because those 2 ohm resistors are in series and identical, only because they're identical, they split that 4 volts into 2 and 2 volts. If it was like a 1 ohm and a 3 ohm, it would split it into 1 volt and 3 volts. 1 plus 3 would equal 4. But yeah, anyway, that's a good good combination circuit. Probably see one similar to that. I mean, not this one, but you know, something along the same lines. And I'm pretty sure, for the most part, all the answers work out pretty evenly with integer answers. So you should be able to. You shouldn't go down. Don't go down some rabbit trail where it's like 0.4932 or whatever your current. Okay. Shouldn't even really need a calculator for most of the problems. Those are combination circuits with resistors. What next? Yeah, you want to look at an old test? Sure thing. Let's see, let's go back a little bit. Let's go back to F09. Oh, this is a final yellow. Oh, this is 101. Oh, shoot. Okay, there. Okay, so this is spring '09 and all this stuff. So picking up here, spring '09 with number 13. So for example here, what is the potential across the 8 microfarad capacitor? You should be able to answer this pretty quickly without really putting your pencil to the paper. Because, well, what is it? You know? Oh, what's 36 divided by 2? What is it now? Now! Tell me! 18, right? Yeah, so here I have 36. So I have 36 here, 36 here. I have 36 across both of these. They're identical, so they split it. So I have 18 and 18. Okay, so the answer there is 18. What is the equivalent capacitance of this circuit? Well, the 1 and the 5 give me what? 6. And the 8 and the 4 give me 12. So I have 1 over 1 over 6 plus 1 over 12. That's 2 twelfths plus 1 twelfths, which is 3 twelfths, which is a quarter. So this is equal to 4. I forgot about that. That's a good combination of the 8 and the 4. All right, so that's equal to 4. So the answer here is D. And by the way, if I wanted to know, right, this is 6 microfarads. This is 12 microfarads. What is the voltage across the 5 microfarad capacitor? Now, really I'm asking what is the voltage across this capacitor, the equivalent, The smaller capacitor will have what? The bigger or smaller voltage? The bigger voltage is going to be bigger by a factor of 2, and it's going to have to add up equal to 24. What's that? What two numbers add up equal to 24, one bigger than the other by a factor of 2? 16 and 8. So I have 16 volts, 8 volts. 16, 16, 8, 8 volts. These circuits, if you're good, you only have to put your pencil on the paper. But if you're not, that's fine. Put your pencil on the paper and just work it out. But some of you are at the point where you can just look at them, I think, and see the answer. Okay? More of these. Stop. You're not going to see anything like this. That was all the previous exam. Anything about what is, these are the area of the plates, all that jazz. We had all that before, so you're not going to see that at all. But you might see stuff about wires and their geometry. Anything out stand out to y'all? Yeah, the dimmer switch. When you rotate your dimmer switch, it changes the brightness of your bulbs. The brightness of the bulb is dependent upon the power, right? 100-watt bulb is brighter than a 40-watt bulb. So the power is one thing. But also, in a 100-watt bulb, the reason it has a higher power is it draws a bigger current. So it also changes the current. So a dimmer switch changes both the current and the power, but it also changes the resistance. That the dimmer switch actually changes the resistance in the circuit, and that's what changes the amount of current that comes through. All right? So the voltage is always constant. In a household circuit, the voltage is always constant. Never changes. But those other things can change depending on your device. Things with a really low power rating, what do those have? A big or a small resistance? Right, a big resistance. Think about, a 40-watt light bulb. If it has a low power rating, that means it's not going to use that much current. So if it has a small current, it'll have a big resistance. And you need to have all that sorted out in your mind. Definition of current, you can see something like that. There are no questions about money. I don't even think we did that. We skipped over that question. You can see something like this. You had some homework like this, picking the resistivity. How many electrons pass through the material. You'll see stuff similar to all these things, right? It's what we did. Any questions about? Oh, okay, so with RC, can I give y'all a quick little primer on it? All right, look, there are only a couple things you need to know. A lot of it's on your equation sheet, so just make sure that you're familiar with that equation sheet. And if you look at your equation sheet, it gives you the equations that you need for a charging and discharging capacitor. Now, it will tell you in the problem whether it's charging or discharging. For a charging capacitor, it's going to look a circuit that will look like this. It'll have a battery in it, it'll have a resistor, and it'll have a capacitor. Say this is 2 microfarads, 3 mega ohms. And I'll always give you a micro and a mega combination because it makes your time a lot easier, because the micro and the mega cancel out. 10 to the minus 6, 10 to the positive 6, they just cancel out. It just makes your math a little easier. And then you also need the voltage, 12 volts. And then I ask you, what is Q at some time? Or what is I at some time? Or what is V at some time? What is the charge, current, or the voltage at some particular time? If it's charging, you're going to use this for charge, this or this for voltage. Notice, charging, charging, charging. If it's discharging, the discharging circuit would just have a capacitor and a resistor. In that case, you'll use this, this, or this. Okay? You need to know how to use these equations, and I can do an example in just a second. But you also need to know what the functions look like. So for a charging capacitor, the charge versus time looks like this. And this maximum charge is equal to CV. That is, CV is this Q. Q is equal to CV. That's the maximum charge you'll get on that capacitor. For discharging, all these discharging functions look like this. whether it be Q, I, or V, they all look like this versus time. So if I have this e to the minus t over rc, it's going to be a declining exponential function. If I have a 1 minus e to the minus t over rc, it's going to be an increasing exponential function. Okay? Now, if you have to calculate, which you will, I do ask you for either the charge, the current, or the voltage at a particular time. Just make sure that you do it once or twice before you come into the class. Make sure that you can use your calculator for that purpose. So let's say that I'm doing a discharging with my 3 megohm, 2 microfarad. What is the charge at 2 seconds? That's what I would ask. And you would say, well, Q is equal to big Q times e to the minus t over rc. And you just put in your values. Big Q is equal to c times v times e to the minus t over rc. And you say, gosh, there is no v, so what do I use for v? V will be given in the problem. It's the voltage of the battery that charged up that capacitor. So let's say that it was this one. It was 12 volts. So that's 2 microfarads, 12 volts, e to the minus t, which is 2 seconds, divided by RC, which is going to be 6 seconds. RC is the product of this and this, 3 times 2. And again, the mega and the micro cancel out. So if you haven't done this, just try doing this. It's going to be 24 times e to the minus 0.3, or 1/3. I get 17.2. And that is in microcoulombs. Your exponential button is e to the x. E, of course, is just a special number. It's usually a second natural log on your TIs. If you have a TI. Y'all got that? Yes. Okay. You can see different things, like it could be charging instead of discharging, in which case you do the 1 minus e to the minus t over rc. There are 2 problems like that. One of them is you have to calculate it, and then the other is you have to identify the plot that describes the charge or the current or the voltage when it's discharging or charging.
So when it's discharging, you use the other formula, basically.
Right. If it's discharging, you would use, well, this was discharging. If it's charging, use this one.
Yeah.
Yeah. Watch your order of operations. Make sure you get your parentheses in there right.
So they're going to ask if this is a charging or discharging. You have to look with the future.
Right. I'll tell you, I'll give you a bunch of plots, and I'll say identify the plot for the charge on a charging capacitor, or the current on a discharging capacitor, or whatever. There are really only 2 options, right? It can either really be this or this, and this is only for a charging capacitor. And if you forget, look at the function. This function is an increasing exponential. This function is a decreasing exponential. If you know your exponential functions, that'll help. But if you don't, just do this. And I'll give you some other variations, right? You can draw these in all different sorts of ways. Okay? 2 questions on that. I think just 2. Is that what I said? Do you remember? I'm pretty sure it's just 2. All right. Let's just sort of keep going through. Well, let's look at another one, actually. Okay, so holler if you see anything. How much energy? That's just the 1/2 CV squared. You could see something like that. I don't remember. No potentials, charges, stuff like that. Yeah. Let's look at, any questions? Particular questions?
I guess I like to do more of these charges.
these charge. Circuits
Yeah.
for capacitors are resistors. Okay, let's do a few capacitors. Y'all okay with that? All right, let's look at this one. What's the voltage across this capacitor? I have a 1 and 1 in parallel, so I start there. What is that? 1 and 1 in parallel is what? Is 2. For capacitors, I just add them up. So that gives me a 2 and 2 in series. So hopefully now you can tell me what is the voltage here. It's 5, right? Because I have 2 and 2 connected to a 10-volt battery. So I have, because they're identical capacitors, only because they're identical, I get 5 and 5. And if I have 5 across these two, I have 5 here and I have 5 here. I don't think there are any others on this one. Let's go. We'll do some resistor circuits too. Let's just find another capacitor circuit. Oh, this is a good one. What's the equivalent of this one? Well, you start first with the smallest, either series or parallel, and in this case, that's going to be the what? The 2 4s, right? And a 4 and 4 in series for capacitors is 2. So I have 2 microfarads here with 2 microfarads here. A 2 and a 2 in parallel is 4. 4. This whole thing, these 3 capacitors are 4 microfarads. Combined with the 4 microfarad is 2. Let me write that down. Here I have 2 microfarads. 1 over a quarter plus a quarter is a half. That's 1 over a half is 2. Then I have 2 and 2. This is 4 microfarads. And so I'm left with 4 and another 4 in series with 12 volts. And now I want to know what is the potential across this capacitor. Well, what is the potential across these capacitors? The 2 4s. Lathan, what is it? No, it's not 2. I have 12 across these 2 is 6. So I have 6 volts and 6 volts. If I have 6 volts, that means I have 6 volts across these 2 branches. So I have 6 volts across these 2 and 6 volts across this one. The problem is asking about this one. So what is the voltage here? 6 volts, right? 6 goes across both of these. What is the voltage here? 3. Right, because I have a 4 and a 4, they're identical, so they split that 6 volts. All right. So you'll have a couple questions like that. Let's see if we can pull up. You know what the charge is on the 3 microfarad capacitor here? A couple ways you could do this. Just take a second and think about it, and I'll show you the 2 ways. It's not 8. You're thinking voltage, not charge. I want to know the charge. 24 is the right answer. Look, I can take the... You were doing it a different way. You were saying, well, this has to have 8 volts and this has to have 4 volts. And that's a good way of thinking about it. And then you say 8 times 3 is my charge, which is 24 microfarads. Another way to do it is to say that the equivalent of these 2 is 2 microfarads. And it's as if it's hooked up to a 12-volt battery. Forget about the one in between, remember, because parallel branches are independent of one another. And so I have 24 microcoulombs. That's C times V is equal to Q. 24 microcoulombs, 2 times 12 is 24, which is what we find up here as well. All right, let's look at what was this? Spring 11, exam 1. Let's look at exam 2, spring 11. All right, there's a multi-loop circuit. You want to try this one? Okay, try this one out. Which of these equations is correct? Now, always, just a hint to you, always put them in order as they occur in the circuit. So you just find that first element and then start going in the right direction. Now here we're looking for the correct one. Let's take a look. She thinks it's B, so I'm going to start here. I'm starting here because I have 6 plus 6 minus 8I1. Let me zoom in just a little bit so you can see better. So starting here, looking at B, I have plus 6. I have to go in that direction to get plus 6. Minus 8I1. I'm going with the current, so it is negative. Plus 2I2. I'm going against the current, so it's positive. And notice I am getting I2 in there. Minus 12. That is correct because I'm going from high to low. Minus 4I1. And it is negative because I'm going with the current, and it is I1. So B is the correct one. All the others are incorrect for various reasons. Is that look of consternation, gosh, I really got this? Or is that, this test? Y'all feel okay with that? Okay, let me clear this. We'll look at it another exam. And then also, here, if I2 is 2.45 amps, what is the magnitude and direction of I3? Well, here I gave you I2, so we're going to do the right loop. Because I already know what I2 is, I just have to figure out what I3 is. And so I just write the equation for the right loop. That would be 12, starting right here and going in this direction, minus 2I2, minus 3I3 equals to 0. And then I would plug in I2 equals 2.45. So I'd have 12 minus 4.9 minus 3I3 equals to 0. That's the other way you can make this a lot simpler, is I just give you one of the currents. Otherwise, you got to solve the whole darn thing, and that's a pain in the rear. Okay, can I clear this? All right. What is the equivalent of this circuit? And then what is the potential across R3? I'll give you about 20 seconds. Did you say 4? You're thinking capacitors. Don't think capacitors, think resistors. Yeah. Be careful. Fortunately, the capacitors come first and then the resistors, so you can switch gears. All right. 1 and 1 is 2. 2 and 2 in parallel. 1 over a half plus a half. That's 1. And then so this 1 and 1 right here is 2. So I have a 2 and 2 in parallel. It's not 4, it's what? It's 1, right. Be careful, okay? Capacitors and resistors. If you're thinking capacitors, you got capacitors on your mind, and then you get to a resistor circuit, it's going to mess you up. So be careful. Like I said, you'll see the capacitors first. They're right at the beginning of the exam, and then the resistors come a bit later. So that'll help a little bit. What is the potential across R3? R3 is this one. You might be able to tell me right off what that is. What is it? It is 6 volts, right. This is a 1 ohm resistor right here. So I have a 1 and a 1. Across this whole branch, I have 12 volts. I have 12 volts across this branch up here too, because they're hooked up to that 12 volt battery. So because I have a 1 and a 1, I have 6 volts and 6 volts across this thing. So I have 6 volts and 6 volts there as well. In fact, I have 6 volts across every resistor in this circuit because I have 6 volts up here and 6 volts up here. Okay? Going away? Need to know about if I remove some things. So for example, if I remove R3, what happens to the current through R1? If I take out this resistor, what happens to this resistor? And the answer is nothing at all. If I have two parallel branches and I change one of the parallel branches, nothing happens to the other. They're completely independent of one another. That's the great thing about parallel circuits. They're independent of one another. However, there was another question. Which resistor has the least current? What was it? I think we did this question actually. R1, 3, or 5? It's going to be R3 has the smallest current. My whole current comes here. It splits into two pieces, in this direction and this direction, and then it splits into two pieces here as well. So I get the smallest current through here. Let's see here. Sure you know about this. Make sure you know your circuit breakers, GFCIs, and your grounding, what their purposes are. Particularly, well, for the circuit breaker, know what it does, but then also know how to do this type of problem. There's one in the homework like that as well. Also, you're going to have, I'm pretty sure you have a question like this, where I just give you a bunch of statements, and you have to pick out the ones that are true or not true. I mean, they won't be these, but they'll be something similar. The household circuit is a parallel circuit? Sure, that's true. All devices operate at the same current? No, they all operate at the same voltage. As you add more devices, the potential across each device decreases. Is that true? No, they all operate at the same potential. And is this true for a circuit breaker? Number 4? No, that's for a GFI, or GFCI, the ground fault circuit interrupt. The circuit breaker turns off if your total current exceeds some safe amount, 15 or 20 or 30 amps, whatever your circuit breaker is rated for. No, I didn't pull any from the concept course because of the, no, sorry. Okay. All right, that's it for that one. Anything standing out to y'all that you want a little extra practice on? Is this useful for you? Okay. Yeah, you have to be careful with resistors and capacitors. Usually we have them on different exams, but you know, y'all are super smart, so we put them on the same exam. Y'all seriously are like, you're the best class I've ever had. I look at your grades and the stuff that we cover, and you have the highest averages, you have the most material covered. Y'all are, man, y'all are awesome. That's what I think. All right. Anything else, y'all?
One question.
Under?
Someone asked me about it, and I've just figured it out. I'm pretty sure it's simple. It was the voltage across an ammeter is small, or the voltage across a voltmeter.
Oh yes, this is on the test tomorrow. So for ammeters and voltmeters, you need to know a few things. Let's just sort of put them in a table. Ammeters, voltmeters. All right. Ammeters have a small resistance. Voltmeters have a big resistance. Ammeters are hooked up in series. Voltmeters are hooked up in parallel. Ammeters draw a very small current. They have a small current. Oh wait, no, I'm sorry. No, I'm sorry. They don't have a small current. They have a small voltage. Ammeters have whatever current you're measuring. If you're measuring 2 amps, they measure 2 amps. If you have 200 amps, they measure 2 amps. So they might have a small or a big current, but because they have such a small resistor, they have a very small voltage. Voltmeters, on the other hand, have a very small current. Right, because if I have a voltmeter, I hook it up like this, my current comes through the circuit, and practically all the current goes through the resistor, and just a little bit goes through the voltmeter, just a tiny little bit. Because the resistance is so big of a voltmeter, very little current is going to go through it. Just enough to make the dial move. Tiny, tiny amount. Okay? Those are the three things for each of those you need to keep straight in your mind. Small resistor, series, small voltage for an ammeter, big resistor, parallel, small current for a voltmeter. There is a question, I'm pretty 98% certain there's a question about that. I'm pretty sure it made the final cut. Okay? Practically everything's on the exam. I sent you that distribution. That's every topic that we've covered. That's good, right? So that way you can walk out saying, I have mastered every topic in chapter 2B, 3, and 4. Okay? Anything else, y'all? Okay, I'm going to wrap it up unless there are other questions. Should I turn off the thing? Is it that personal?
I mean, it's not that personal. It's
Okay.
just that
The quiz, I understand there were some problems with the quiz. Is that what you're wondering about? Yeah, I'm sorry about that. I'm going to make it right.
because one of them says 1 to 3 meters.
I know, and I usually fix that, but I was in a hurry when I put them up and I just didn't correct it. You know what I'm going to do? 10s for everybody.
Really?
Yes.
Yes.
Okay, good.
Okay, because you asked. No, I'd already said I'm going to do that. Okay? I'm sorry about that. That was my mistake, and I'll fix it. And I understand there are some issues with Moodle, too. So